Hi and welcome to Module 8, Analysis of Chemical Ideas, and Video 3 today. And today we're looking at infrared spectroscopy. So what is it? It's a really useful technique that we've got, and it can tell us whether there is any bonds or functional groups that are present or absent in a compound. And it has really great applications in industry for monitoring chemical pathways, forensic examinations, drug development, and in some quality control, telling us what may be present or not present in a variety of samples. It too can be used to analyse solids, liquids, or gases. Now, it has a lower energy and a longer wavelength to UV and visible radiation. So if we again imagine our electromagnetic spectrum, it is on the right hand side of our UV and our vis, heading towards our radio waves, so the waves are getting longer and the frequency less. Now, the energy from this radiation is not enough to promote the electrons to a higher state, but it is enough to change the vibrations there. So we've got a couple of different modes. In our diatomic molecules, such as oxygen, we can have them vibrating backwards and forwards, but in polyatomic molecules, there's a lot more that can go on, and the general vibrations can be shown here. So looking at this slide here that we've got, and it'll show it in a little video. You can see here we've got symmetrical stretching. So like the man said the other day, his arms are going out in a symmetrical fashion. I'll play that again. You can also, and I'll pause it there, see the wagging of our asymmetrical stretching. So it's like one hand up, one hand down. Play it again. Scissoring, open, closing, waving, kind of wagging. A whole host of movements that can be taken there with our atomic vibrations that we can see. So moving on from that, how can that help us there? So the energy then that is absorbed by those atoms depends on the bond length, so how much it can move and so forth, the strength that it has, and the atom size. So heavier bonds will require more energy to increase their vibration, which makes sense. Double bonds will require more energy again than single bonds to help with their vibration there. So what we can do is measure the absorbance, and that'll tell us what bonds are present by what is being indicated in our spectrum. So unlike other graphs and so forth that go from the bottom up, our IR spectra actually move from the top down and are forming a series of troughs. So how do we interpret? We're looking for certain troughs. Now there's a whole host of those troughs. There are some to the right hand side of less than 1500, and that's called our fingerprint area. It's unique to the compound, and the only way we really use that is if we have a sample of what we think it is, a known, and we can compare it to there and see, do they overlap and do the fingerprints match? But what we can often do here is we can pick out certain things that we know exist. So of course we're dealing with organic chemistry, so we are going to see CH bonds, so they're not overly helpful. We already know it's, or pretty much know it's organic. If we don't, I suppose that presence of the CH bond is useful, but if we know it's an organic substance, it's not telling us a great deal of information there. So in the case of heptane, the main bonds we've got are the CH stretch and bend. Here we've got methanol, so we're thinking CH bonds, and we're also thinking that we have a C bond to an O, where it attaches to the O and then the O to the H. So here we have a broader band, and it's a characteristic broad band at around this sort of 3,400 region. So if you look across here, it's quite broad. Here will be our CH bend, but we know that that exists. And here's another complementary one for that C to O bond. Now here in propanone, again, C to H bonds, what we're expecting to see is a C double bond to the O, and that's characteristic around that 700 spot that's there. So this is the data that you will be given in your data sheet. So you don't need to know all of those numbers. They will be given to you in this table. You just need to know what you're looking for and what to find. So here again, our amines that we've got our OHs, the C to H bond, we're expecting to see those, and so forth. So let's have a look at this example here, and we've got the infrared spectrum of an unidentified compound, but we do know its molecular formula, and it's C2H4O2. So what have we got here? So again, we've got quite a broad band around that 3,200 spot there. So that's likely that we have got an OH bond that's there. Looking at our spectrum, so let's go back, and it's probably best if you have them beside you there, so we can look at some of those there. We'll just move forward again and see what we're finding. So we've got something here, 15, probably about that 1700 bond there. So if we look at what's around that 1700, we've got a C double bond O that's in there. And then we're moving down into this region here. So what have we got? So with C to H bonds, a C double bond to an O and a big OH bond, it's likely then that we have got a carboxyl group. So with C2, our carboxyl group is likely to be ethanoic acid. We'll practice more of these in class. We've already done a few from our visit to the TAFE, but we'll practice a few more and we'll be an expert in no time. Talk to you tomorrow. Bye-bye.